All right, so first I want to start by just introducing my panel. So I have John Fastabend from Intel, Rony from Mellanox. We've got Ethan Jackson from UC Berkeley, he's doing his PhD, and I've got Nic from Netronome. So to start off and provide a little bit of context, I want to do like this thing where we see this well-known slide where so in OVS, the first packet typically goes through the data path up to the OpenFlow protocol implementation. We compile down a flow of all of the relevant matches that we want to do for those packets, and then a set of actions to perform. And then those will be pushed down to the data path so that subsequent packets can be entirely handled in the data path. So if we take a closer look at that data path, the main operations it needs to do is some sort of parsing and classification of the flow. We do a lookup in some tables. If we find a flow that matches, then we will execute some set of actions. And those actions may end up resubmitting back to the start of or recirculating back to the start of the pipeline and going back to classification. And then if our lookup fails, then we'll do the upcall, and that's how that first packet gets handled. And then subsequently, a flow will be installed so that later packets won't need to miss that lookup. So when we start to look at hardware offloads, there are a variety of different ways that you could offload bits or all of this data path operation. So the first one I'm going to look at is partial offload, which is where we take this pre-classification step where you extract the headers and maybe you do some sort of hashing. So if you, actually this kind of links back to what Ben's talk was about. This is this first expensive per packet overhead. And so if you can offload that to some piece of hardware that can do it more efficiently, then that will speed up the rest of the data path. And even if it just provides a hint to user space about the lookup, then it can be accelerated, it can go faster, and then quickly find the flow that it needs to execute, and will execute a set of actions. So then there's a case of full offload, where you're actually taking all of the data path functionality down to down to some sort of NIC. And obviously still there needs to be some sort of path to do an upcall. But in this case, your classification, your lookups, all of your action execution needs to live in the data path. So there are a variety of different data paths. So today we're supporting user space data path, which is commonly used for both testing and also for the DPDK implementation. We've got the Linux OVS data path that's configured through the netlink protocol, through the kernel. And then there are two proposals that are in different stages. So William talked earlier about eBPF implementation of the kernel data path, and you can see the benefits from that. And then there's also a set of patches on the mailing list for implementing a data path through the TC Flower interface. And Rony will go into that in more depth. So if you consider all the possible ways that we could be offloading the OVS functionality, so there's a partial offload where maybe a hint is given. This could work with the user space data path or the Linux data path. So Ethan will go over that in a bit more detail in a moment. You saw earlier the Netronome talk where they took the OVS Linux data path and transparently offloaded that to their NICs. And like I said, the Flower proposal is on the mailing list. And there's also a proposal to take the eBPF data path that's being worked on right now and perhaps even push that down to a NIC as well. So with that, I'm going to hand it over to Ethan to give some more description on the partial offloads. All right.
Hey. All right, cool. So I'm Ethan, and I'm from UC Berkeley. And I did some work on a paper called SoftFlow in collaboration with UC Berkeley and VMware while I was still working on Open vSwitch there. SoftFlow itself is about how to build middle boxes in Open vSwitch, so fairly complicated software pipelines. But as part of that work, we suggested a method to offload packet classification to a NIC to accelerate performance. So I'm going to go over that really quickly. All right, so the high-level idea here there's somewhat of a trade-off in networking generally between pure software implementations, which are highly flexible but relatively slow, and pure hardware implementations, which are rigid but fast, obviously. And the goal with SoftFlow is to stake out the middle ground here. And the basic idea is that for the workloads we care about, when we profiled the switch, we would see the vast majority of CPU time was spent just doing packet classification, 80–90% of CPU time for data center workloads. So the idea is that we're just going to offload packet classification and get this really significant performance benefit, but we lose nothing in terms of flexibility. You can still have all of the features that OVS provides. You have no limits on classifier size, all this sort of stuff. So in terms of the implementation, we treat the NIC just as a flow cache. Next generation NICs have TCAMs available on them. We had sort of experimental NICs from Broadcom and Intel. And we choose the sort of 50,000 most used megaflows in the software datapath. We assign an ID to them, as Joe suggested, called a hint. We put those in the NIC. When a packet comes into the switch, the NIC classifies it, gives us the hint for what megaflow should apply, and then the software can just look up the hint in a table. And this has a lot of really nice advantages. Specifically, if the NIC's TCAM is much smaller than what the software TCAM would support, then you just don't offload all of the megaflows, and the hint will be null, but you can still fall back to software packet classification. Or alternatively, if the NIC TCAM isn't as wide as the software switch, it doesn't support all the fields that we care about, then you can just offload those fields that the NIC can classify over, but still fall back to software packet classification if necessary. So in summary, this is, in our evaluation for the research paper, we saw somewhere between a 5 and 90% performance improvement on complex pipelines. We were doing like AES encryption, connection tracking, NAT, but we were still able to benefit from TCAM offload, and we were able to do this without sacrificing the flexibility that software gives us. I think that's all I got.
Yeah. So next up, we'll have Rony from Mellanox giving some elaboration about what kind of offloads that they're using for Mellanox.
Okay. So in Mellanox, we call those acceleration ASAP square for accelerating switch and packet processing. So we have kind of talking also this on the two way. Taking all the thing to the hardware, we call it direct. That's using the SRV. So all the classification, the forwarding, and everything is going into the hardware. And as Ethan suggests, you use a flex just to do the classification in the software, and then the software continue to forward the packet. I will start talk about the full switch offload, called direct for us. We call it direct. So as Joy mentioned, the OVS is already maintaining a user space and a kernel module. What we are ideally suggesting to have another layer, that is a hardware layer, and we want to maintain the same rule, or most of the rules that's going into the was in the beginning meant to go to the kernel, to go directly to the hardware, and then the hardware will do the offloading, the forwarding of the packets. So the idea one was to use, as we already pushed to the kernel, all the TC flower classifier. So currently you can use a TC rules to forward the traffic between ports. We already push all the things upstream. And now we want to use the open vSwitch to control it. So the idea is to use, you see the blue point and the blue box inside the OVS. What we want to use, we're using the DPIF layer, and we want to continue using the old one, the Netlink DPIF, So what we're doing, we add another layer. It's not another layer. We're using another DPIF that is holding the old one, the netlink one. And the idea is that for every flow that is going from the down inside the vSwitch D from through, it was in the beginning supposed to go to the kernel. We have a we just ask the policy, do we want to take it to the hardware? If you want to take it to the hardware, you're going through the TC on the right side, and we take it down to the kernel. And then from the kernel, it's going directly to the hardware because the TC use software, it's kind of a TC flow classifier that you can specify that you want to take it to the hardware. So it's a hardware only. So it's go directly to the hardware, and then the forwarding of the packets it's happening inside the hardware. In any case that the hardware is not supporting it, the error, it return error. The driver is returning an error, and then we take it directly. We take it to the normal, the old one, the kernel data path, and then the packet will be forwarding by the software. So we are supporting a failure. Any case that the hardware is not supporting something that can be done also in the software. So we already submitted, and it was an RFC. Now it's a code. It's just 10 patches, and it's already in the OVS mailing list. You're welcome to comment. So this is about the full offload. We have a demo that we demonstrate an OVS with VXLAN offload, and we get about 25, that is forwarding to a virtual machine, and inside the virtual machine we have a forwarder that is forwarding to the second port. Everything is, in the VM we run DPDK, because if not, the kernel is not handling those kind of high packet per second, and we get about 25 million packets per second forwarding without any CPU interfering in the host. So that's the reason why we want to offload, because right now, if you saw the numbers, there was a few hundreds, a single number of million packets per second, and it costs some cores, and we're doing it with any need for a core in the CPU. And as Ethan mentioned, there are problems that usually people things that the hardware is not doing, and in this case, we want to do a partial offload, so to take only the classification, and because every switch need to do, like Open vSwitch is doing classification, doing an actions, and then a QoS, and then transmitting the packets. So we want to do the classification inside the hardware, and also the drops. So for example, what we're doing, if it's using DPDK, or it's also can done when using the OVS data path in the kernel. The idea is to use a flow ID. So you can figure for every mega flows that is going inside to the kernel or to the DPDK, it's in the DPIF level, we want to use to take the classification to the hardware. So if it's a DPDK or a TC inside the kernel, so this classification, we give it just a number. It's in every packet that will hit in this classification in the hardware, you will get inside the completion. So if the kernel, it will be SKB mark. If it's a DPDK, so it's another field. So you get a completion. In the completion, you get what's the hardware classification that was hidden, and then you can do directly the actions that need to be done and forward the traffic. Of course, when we want to drop a traffic, I think in XDP we are showing that we can drop about 20 million packets per second with a single core. We can do it inside the hardware. We don't need to take the packets into the software in order to drop it. So if we know that this specific classification need to be dropped, it's the easiest way to put it to dev null and to drop it. I think what currently is missing, and we added counters. So because in order to maintain those rules in Open vSwitch, you want to have a counter for this drop. So we need to have a counter for each flow. And so we have it now in the TC implementation, and that's one thing that we're working now to add to DPDK. So we are also working on the DPDK. There is a new interface in DPDK that is called generic filter, because all the DPDK implementation right now was very, very specific to hardwares. And neither of them has a 12-tuple classification, and you didn't have a counters per flow. So we're pushing the community to that direction. And I think it's supposed to come out in next year, early next year. And that's all.
Okay, thanks, Rony. So next up, we've got Nic from Netronome.
Who? Yep.
Who's pointing behind you.
Hey guys, hey again. So I'll just quickly run through what our considerations are for offload. So as I said earlier, I'll run through this again quickly. We've got fully programmable 72-core SmartNIC with 576 threads running on there. We have about sort of TCOs around 6x reduction. That's sort of our case for acceleration. Obviously, you get more VM instances, you get higher throughput, you get lower latency. And our current implementation, which we really focus on, is the OVS datapath offload. So we offload the kernel datapath at the sort of megaflow DPIF level, and we have this with or without contract. So we have a contract implementation that's already there. I'll talk about this more in a second. And the key things for us really are that we want to, with this, is we get a feature-rich full offload. So we offload almost all the OVS match actions, including tunnels and contract. And we have a fallback path. So that means that we have sort of selective acceleration. And I'll dive into what I mean by this a little bit more, which is that if you have a megaflow, let's say you had, this is a very simple example and probably not a real life one, but let's say you had an IPv4 megaflow. And you have, within that, you have ARP traffic. So we could potentially offload other parts of that megaflow, the other IPv4 traffic, without having to be able to offload the ARP traffic. So we would actually push that and have this sort of I've called it almost partial fallback. So we want that selective acceleration, which allows us to accelerate individual packets. And obviously we're ready for eBPF-based OVS. We have an implemented transparent eBPF offload, both for XDP and TC, and that's already upstream. And as I've alluded to, our key requirements are just that acceleration should be transparent and feature-rich, without unduly limiting capacities and update rates. Now, what I mean by update rates there is we have, obviously, with Netlink, you can get limited. You can end up with a very low update rate in terms of a few thousand flows per second. With TC, from some of the testing that Mellanox have kindly done for us, we can see it's about 32K per second right now. We're hardware limited around actually a million flows per second. So to be able to get up to those kinds of update rates with something that can go through the kernel would give us a huge advantage. And that's something which we're really looking forward to. And then also the final thing is, again, stateful firewall and contract is something that's key for us. Because you get huge performance benefits. Doing this in the kernel can hit you a lot, depending on your use case. So being able to offload that is something which we're seeing a lot from customers, and there's a lot of push for that. Obviously, there's a lot of proposals up in the community at the moment. There's stuff with TC, which is great, and a few other things. Obviously, we've posted our patches for our kernel datapath offload. and really being able to push this through in the community so that we have a very transparent, clear in-tree solution for offload. That's really our key priority, making sure we get this into the Linux kernel tree, making sure this is all in-tree. So here's the first offload model. I briefly spoke about this earlier, but just to go into more detail. So the way it works at the moment is we have hooks within the kernel data path. So what we actually look for is we look for the individual flows. We see when a flow gets pushed down from the OF proto, and we actually will then decide whether we can offload this or not. So basically, we offload pretty much everything. Up until recently, we didn't offload mirroring. We can now do that. And something like ARP, we would probably still leave up there. So if we saw something specific which we wouldn't offload, we leave it in the fallback path. Everything else comes down into the NIC. Within the NIC, we have sort of our basically the same as the sort of standard megaflow tables for your standard OVS within the kernel. And then we also have, as I mentioned earlier, the exact match flow cache at the front. That can contain up to about 4 million flows. So we can offload a very large amount of flows running all at once. And with the contract module, we offload that. We have a separate hook within contract, which pulls that down into the NIC. And we still fall back for specific type things within contracts, so things like FTP and so on. We still use the helpers within the kernel. So again, this partial offload helps us. Offload, some performance numbers there, which help us. The eBPF acceleration, which I went through in the past already. And then just finally, this is the sort of key points for us. In the short term, we're looking at OVS kernel data path acceleration. So we're adding features to TC Flower. We're working on our own solution, which is the kernel data path, where a lot of the features we already need are already there. And then in the long term, obviously, we can accelerate eBPF and support eBPF-based OVS. And our priorities there, again, are per packet fallback path, contract, high flow capacities, and rich offload.
All right, thanks, Nick. So finally, we have John from Intel to give us a bit of a higher level.
Let's see if I can go forward here. Backwards. All right, my name is John Fastabend. I work for Intel. I think these kind of covers the 3 different modes that we were considering as well. So instead of creating another deck, I thought I'd give a little high-level overview on how we got here, why we're interested, etc. And an interesting point, I think we gave OVS offload talk in the first OVS conference, or maybe the second in 2014. So it's quite good to see that, A, we have patches now on the list, which is a huge accomplishment. On the OVS list, we have patches in the Linux kernel to support this now, also good. And I think there's some DBDK patches in the works, or there are initial proposals are out. So I think we've done, actually accomplished something in 2 years. So I feel good about that. The other thing I wanted to just sort of say from a high level is this is kind of where we started, right? You have a NIC at the bottom. It's connected via some bus to your CPU. And then in some language, and if your language isn't there, I'm sorry. It's because Google didn't have a cool animal for your language, and you should get on it. Okay? All right. So OVS is GCC, and I don't know if CLang works with OVS these days or not, but I hope so. It's getting close. The guys up here who know are nodding, so that's good. So this is kind of their standard thing. And when we started, your NICs did sort of basic stuff, right? They did TSO, flow control, checksum offloading, C tags, S tags, maybe DDIO if you got a good chipset. Intel guy speaking. So that's kind of where we started, I think, 2-3 years ago when we started taking this on. And then on the CPU side, you have a set of instructions, your SSE, AVX, FMA, these kind of advanced instruction sets. Okay, so the point I wanted to make here is that those are offloads, and there's a group of folks that are kind of working on the Linux kernel to make sure those work for you. And they occasionally don't work. So when you hear people say transparent offloads, I want to point out that there's a group of folks that are kind of busily working in the kernel, fixing bugs, and occasionally we still see bugs, and we fix them. So like any sort of new offload, we can kind of expect that this effort is going to require some amount of kernel lift, and we can expect to see some performance improvements for that work. All right, so here we go. Now, what happened, at some point, we decided to add SRV support. It's been there for quite a while, but when we start to think about 10 gig NICs, it becomes more important because the data movement cost starts to go up. When we talk about 40 gigs, it starts to go up higher. And now we have 100 gig and 400 gig on the roadmap, and IEEE is working on 400 gig now. And the question is, how do you keep up with the data movement and the processing that's needed for 400 gigs, right? So we have the driver guys and the CPU guys working on 40 gig and 100 gig now. They're going to probably do fairly well at getting that down. But it's still going to be hard to compete with a direct connection into a virtual machine if you need that sort of data rates. When we get to 400 gig, it's going to get even more challenging. So I think this will become more and more relevant over time. And the last thing I would like to say is just that there is a lot of sort of innovation going on in this space today. So on the hardware side, we have the DBDK flow classification. We have P4, so we're seeing more and more flexible hardware to sort of back up this idea that you want to use SRV. We have NPUs and FPGAs if you want to start offloading state. And then in the Linux kernel, we have things like TC, which are now becoming more and more hardware friendly. Also on the CPU side, we have sort of this infrastructure being built to support this. So we have VTD, VTX, eBPF, and XDP, which we also talked on XDP earlier today in sort of the Cilium context. We have advances in data structures, so there's a group of folks working on cuckoo hashes and all these kinds of fun things, and I think we have a talk about that later, maybe tomorrow or something. Not specifically cuckoo hashes, but building better data structures. We have encryption, APIs, and SIMD stuff that's going on in the user space side, and hopefully in the kernel side as well at some point. And then on top of all this, we actually try to remember that people have to use this. So in the XDP case, we're building verifiers so that we can't crash the kernel. There's a large group of folks that we benefit from, even though we don't directly see them in the OVS community working on GCC optimizations, CLang optimizations. All that helps. And the runtime environment so that this can be easily deployed, your distributions, and all that. And that's all I would like to say. I think we have some questions.
Yeah.
So, all right, thanks.
All right. So actually, I want to start with you, Rony. So you presented a couple of different models, both the sort of, I guess, partial offload, if you will, the DBDK-based stuff, and also the full offload using Flower. So do you think that, I guess, from Ethan's slides, he was saying that in complex data center networking cases, maybe 80–90% of the processing in a server is the classification. So I guess, would you be able to expand on why is the full offload necessary, or why is it more interesting for customers? Nic, do you want to?
Okay, I'll take it first. What we find is in production use cases, so we've tried this out now with various people, various customers. We do find that, especially when you get into things like tunneling, you get into more complex actions, especially when you start, so for data centers, that kind of stuff applies, but then especially when you get into carrier world, then suddenly things get very, very complex. And we find that at that kind of point, we're actually, in those kinds of use cases, more than 50% of our traffic is actually actions and so on. 50% of our workload. But obviously that depends on your use case. So what Ethan was talking about was if you're in a very, very simple, straight down the line data center. And I think that's very true. So I think we've got to understand that there are different use cases here and different places this stuff gets used. And that's kind of what affects this, what the right thing is to offload.
Okay, yeah.
Yeah, I'd like to make a point too. I think so we're like really focused on performance in general in this space, but there's a separate issue, which is sort of the business side of it, which is, I don't know, from my perspective, for these things to really take off, we need like a wide variety of NICs to support them, which means there needs to be a standard interface, and guys like Intel and Broadcom and Mellanox obviously needs to support that same standard interface. So I think to some degree the tension here is like SoftFlow is trying to make a proposal for something that could be built into commodity NICs and standardized. But if you're willing to take that extra effort that like you've done to sort of highly optimize the carrier case, you're going to get better performance, but it's going to be sort of less general. There's a trade-off there. Yeah.
Okay.
I think the less general thing is a very key point. You have to be, very careful, and this is why we're doing a lot of work now with the Linux kernel, is to make sure that all this stuff is upstreamable and all this stuff is generalized and usable in that use case. So that's where things like with TC-Flower, with the stuff that Mellanox are doing, we're looking to build on that and add a lot of functionality to Flower, because we think that's potentially a very useful use case where it's very general.
Yeah, so, yeah, feel free to go.
Microphone? Okay. So you asked where it's the full offload is required for all the NFV's customers. That's the one to get really good bandwidth, and packet is not bandwidth, more packet per second. So for that, I think we do need the full offload, and that's the customer that's demanded.
Okay. So perhaps this is for you, Rony, again, or John could shed some light on this. So obviously we've got a lot of focus on things like oven and OpenStack use cases. So this is maybe going in a bit of a different direction, but we see stateful firewalling, this kind of thing, as being a major part in that. So do you see like a path to get Flower, for instance, to provide that stateful firewalling offloads into your NICs, or do you see another path for oven hardware acceleration?
So yes, we do look on the contract to take it into the hardware. I'm not sure if it will be, that depends also what's with development on the Open vSwitch, if we'll do through TCO inside from the kernel. We can take both of them down there to the hardware. But yes, we are definitely working on that.
I would just say the problem with connection tracking for a lot of ASICs is that it has state, right? And so I think traditionally a lot of these ASICs have done sort of soft connection tracking where you just monitor the TCP flags and you call that good enough. So, I think that it sort of requires a different, either if you want to use this feature on certain ASICs, you'll have to figure out how to bridge that gap, right? And the other thing is I just say that TC is probably not the right infrastructure to offload it. I think you want to look at actually the connection tracking in the kernel, or perhaps even better yet is look at the connection tracking that's actually being used by OVS in user space and see if we can somehow unify the two connection tracking versions that we have. Right, so OVS, you have one in user space and you have one in kernel space. Is there a way with some of this eBPF and P4 work to unify and have a single connection tracking, and then take that into the hardware? I think you'll have trouble telling hardware vendors that I have two versions of connection tracking, and they sort of live in independent worlds, and they have different features. So I think first I would look at unifying the software version first.
So one of the problems I see maybe with that is that even if it's the logic is the same between your hardware version and your software version, there may still be cases where you need to sort of do some sort of software fallback to your kernel, and then you need to keep them in sync, or reporting stats correctly up to the user space. Yeah, Nic, looks like you've got some thoughts on that.
Yeah, so this is something this is the same problem we run into with eBPF maps when we're offloading that kind of stuff. And so we've proposed some stuff in our NetDev paper to deal with this. And effectively, you have to end up with some form of syncing mechanism. So you have to have an owner fill that map or that connection tracking table, whether that be the hardware or the software. And the other person, if that wants to grab anything from there, so if your fallback path and software wants to grab something, there will have to be some syncing now and again. We spoke to Dave about this at NetDev, and he kind of seems to be behind this proposal for eBPF maps. And it's very sort of synonymous for connection tracking tables. So I think that's probably it's the only approach. We've thought about this for a while. It's the only approach we can think of that's going to be usable and successful in the short term. Long term, there could be other ideas, but that's the only thing we can think of for now.
Okay. Do you want to add something to that, Ethan?
Yeah, I mean, the nice thing about the SoftFlow approach is the state synchronization problem goes away. So we have this rule that when we receive a hint from the NIC, we check that it was correct. So the datapath flow table may have changed and the rules may be out of date. And during the time that it's incorrect, you just fall back to software forwarding for a while. So it has this sort of really elegant property. Obviously, if you're relying on hardware forwarding speeds and you fall back to software for a while, that might be like an issue. But it's one nice thing about this sort of simple approach.
Yeah. So how would you go about debugging something like that? So you just mentioned in a case, maybe in some situation you end up falling back. Like, can you think of how we can design the system to be debuggable so that people trying to use this thing can actually figure out why did my performance just drop?
God knows. I mean, this was a research paper, so it worked.
John?
Yeah, there is a third model where you run the connection tracker in a VM or a container outside of the OVS, and it looks like an action or a port forward model instead. And then from the hardware side, you can just offload that to the port, for example, if you hide it behind a port, and that sort of feels very NSH, like. And works for a lot of hardware ASICs that perhaps don't have state or don't want to have state in there.
So are you suggesting like the NIC in the middle of its pipeline would send the packet to a VM that's doing connection tracking, then it would go back before doing more?
Yeah, I think that's a valid model, right? You
Yeah.
send it to it with some state attached to the packet, and then the packet sends it back with some metadata attached to it. And then your hardware doesn't have to maintain state, but it has to be able to match on arbitrary metadata, which is an easier problem in hardware than to, in my opinion at least, than to deal with full-blown connection tracking state. The other, then there's the question about east-west traffic and performance of PCIe buses. So, we have trade-offs on all these cases, right?
So in that case, maybe it's preferred to do a partial offload, because if you take into a virtual machine, from the virtual machine, you don't want to cross again the PCI to go to a different virtual machine.
I think it's just a trade-off, depending on how much PCIe bus you have versus how much traffic you expect to go east-west, and it's almost a per-use case thing. I think at some point you need to have the ability to configure these things. One of the nice features of having it as a port is it is actually configurable. You can forward all of your traffic to this VM that's doing the connection tracking, and then based on if it's a local or a remote, you can go back to the NIC. You could imagine some split of traffic. High priority traffic goes to the NIC and uses the PCIe bandwidth, so you get an interrupt into another VM instead of having a software kick. These are sort of trade-offs that people have to make as far as performance goes.
Yeah, I mean, the thing is with the pre-classifier then is you're going to have to send it back, because obviously with the recirculation with contract, you're going to run into a few issues when you end up diving back. So that's the kind of the key thing there. That's why the whole pre-classifier will still have to have the packet going back and recirculating around back to the NIC.
I want to make sure that we can open up a little bit of time for questions. I think we have maybe a couple of minutes left.
Let's let it go an extra 5 minutes.
Okay, so if you have any questions, please.
So it reminds me, first of all,
We got the mic working there.
This reminds me of the fact that we tried to do TCP offload and that did not work. And this, because it was stateful, and the same thing happens here. What I want to know is people who are designing not for the research paper, but for the industry, how do you handle errors and how do you report? Because that's one of the main things that people, before it gets adapted, people want to set ICMP errors or want errors to be reported on a per packet. But in this case, the packet could have been completely changed because it went through the flow tables and all the things have been changed. So how do you guys actually implement it?
Is there someone particular you'd like an answer from, or got some?
I can maybe say how we've been handling this is we've been handling it is if anytime there's an exception in the hardware data path, we kick it to the correct software mode. So what that means is if there's an exception in the tunneling engine, for example, we'll kick it to the tunnel bridge in software with a metadata tag that says this is an exception. And then your software logic can handle that exception in some way. Now there's still questions about how do you figure out that you've mutated the data 2 steps before. The hope is that because the data path and the user space path are in sync, that you get this exception and you can backtrack that. I do agree that it's a bit murky, but that's the current handling mechanism.
So the other thing is that would happen with this is concurrent processing, parallel processing with multiple cores. You have multiple cores, you get multiple packets, and how you will coordinate all that.
Nick?
So obviously with 72 cores running at once, we've got quite a lot of reordering we need to do. We have hardware modules before and after all our packet processing. which basically sort out the order of the packets. So that's actually one of the key bits of IP we had to develop to get this many cores working at once. So we have a hardware engine that does that.
I think Bob, yeah.
Anybody really excited to? Yeah. Unless someone else is jumping up, I can take on this one, I think. There's definitely a trade-off. So when you go to the NIC, you consume PCI bandwidth, but you get to use the NIC's DMA engine, right? So, and the interrupts that come from the NIC into the VM. So in some sense, there might be a slight latency improvement in that case. But you're also freeing up your CPU to do other work. Versus if you do it in the CPU east-west traffic, now you're spinning your CPU is actually doing the mem copy, so it's spinning. And the trade-off there is it's hard to make a blanket statement about it because it depends on both your CPU version, how much PCI bandwidth you have, what PCI gen you're using, what NIC you have. So it's quite hard to make some blanket statement about that. I think you have to look at the actual data for your use case, how much east-west traffic, some representative set of data traffic to do that, make that analysis. I don't think it's right in all cases. In many cases, it does make sense. In some cases, it doesn't. Does anybody have a more definitive conclusion?
Yeah, I mean, for us, it just depends on the use case again. If you're doing a bunch of actions, you're doing a bunch of work on the packet, then it makes a lot more sense to send it down because we're obviously offloading a huge amount of work from CPU there.
Got a question over here.
Does the use of organics limit live migration, or is it supported?
Ethan, do you want to take this one?
Repeat the question. So the question was, does the use of hardware offload like SRIOV limit live migration? Right. So I don't know for your solution. For mine, it doesn't. And my sense is traditionally with SRIOV, it's a problem, but with the next generation stuff, it might not be.
Yeah, SRIOV, it is a problem. So we've implemented VirtIO now on our NICs as well. So you've got live migration.
So I'll let you go. Oh.
We're working on that too, but it will take some time, yeah.
Yeah, I've actually got another question for you, which is, so in your model, you've got some sort of a policy offload module, which decides how you're going to actually push flows down to the hardware, or whether you just keep them all in the kernel. So what kind of factors are you considering? And is that something that you would expose, for instance, to a controller, like an open flow controller, or is that something that you see existing purely within the OVS vSwitch D?
Yeah, I mean, I imagine it existing within the OVS datapath only. And it's purely a function of what are the most frequently used megaflows, so what's the most bang for the buck, and what megaflows have been around a long time. In the paper, we just offloaded everything. Okay. So it wasn't really an issue, but yeah.
I can add, I tried to write an OpenFlow proxy once that proxied between hardware and software, and it was I came to the conclusion that OVS is really the only place that has enough knowledge to do any sort of offloading.
So I know that we keep a lot of statistics and stuff in the validation portion, and so I guess that's a place where you could say, well, this flow is clearly hot. It's got however many packets per second arriving. So Rony, do you see any other different?
Yes. So we get some people that is asking, some kind of traffic I want to take in the CPU. I want to give priority from this kind of traffic because this is a gold member that we want to give him a better quality. Those kind of policy that's come from a controller. Sometimes we want to debug, so we spoke before about debugging. So if you want to debug a specific flow, maybe you don't want to hardware offload it. You want to take it into the CPU. You want to TCP dump it and to see where it is. So this is the two cases that we do things that's you want to do the offloading, not to do the offloading, and to control it maybe through a controller or not just inside the Open vSwitch. So that's what we said. The API you saw, we put the policy in the side, so someone can extend it and make it to a controller or something like that.
It looks like that's a pretty good place to conclude. Let's thank our moderator and our panelists.